Tonight, turn your eyes toward the southern sky. If you were standing far enough south, you could find a single bright point of light called Alpha Centauri. It looks like one star. It is really 3, and it is the nearest star system to our own, a little more than 4 light-years away. For a long time, we have wondered whether any planets circle those stars. Then, not long ago, the James Webb Space Telescope turned toward the brightest of them and saw something faint sitting just beside the glare. It appeared once, and then it seemed to vanish. This is the story of that flicker of light, what it might be, and how a patient team worked out where it had gone. The question underneath it is a simple one. Are we looking at the closest planet ever seen around a star like our own sun? Start with a simple fact. Of all the stars in the night sky, one system sits closer to us than any other. It is called Alpha Centauri. The light you would see from it tonight left a little more than 4 years ago, travelling the whole way at the speed of light. In plain numbers, that is about 4 1/3 light years. It sounds close, and in the scale of the galaxy, it is. It is also impossibly far for anything we have ever built. Let me give you a way to feel that distance. The fastest spacecraft we have ever launched move at tens of thousands of miles an hour. Even at those speeds, a journey to Alpha Centauri would take tens of thousands of years. The light that reaches your eye crosses that same gap in just over 4 years. So when we look at this star, we are looking at our nearest doorway to the rest of the universe, and even the nearest doorway is far beyond our reach. That is part of why Alpha Centauri has always held a special place in our imagination. It is the star next door. If there were ever to be a second Earth close enough to dream about, this is where we would hope to find it. Writers have set stories here for a century. Scientists have pointed their best instruments here for decades. The pull is the same in both cases. This is the closest place that is not home. For most of human history, Alpha Centauri was just a single bright point low in the southern sky. People in the southern half of the world have always known it. To the eye, it looks like one ordinary star among many. There is nothing about it at a glance that says it is anything unusual. You would walk right past it. But the closer astronomers looked, the more interesting it became. That one point of light turned out to be more than one star. The stars turned out to be remarkably like our own sun. And the whole system turned out to be a near-perfect target for the question that drives so much of modern astronomy. Are there other worlds out there? And could any of them be like ours? For a long time, that question stayed open here. We knew the stars. We did not know if they had planets. The 2 brightest stars in the system in particular kept their secrets. Every time someone tried to look for a planet around them, the glare of the stars themselves got in the way. It was like trying to spot a firefly sitting next to a lighthouse. Then, recently that changed. A telescope unlike any before it turned its mirror toward the brightest star in the system, and in the data that came back, after the starlight was carefully stripped away, there was something. A faint point of light, sitting just to the side. A possible planet, around the closest star like our sun. That single faint point is what this whole story is about. We will take our time with it. We will look at the stars first, then at the telescope, then at the discovery, then at the strange twist that followed, and finally at what it might mean. There is no rush tonight. For now, hold on to just one idea. The nearest star system to our own may have a planet we can almost see, and the road to that discovery is more surprising than you might think. Here is the first surprise, and it is an old one. The single bright point we call Alpha Centauri is not a single star at all. It is 3 stars bound together by gravity, travelling through the galaxy as one family. To the naked eye, they blur into one. Through a telescope, they separate. The 2 main stars are called Alpha Centauri A and Alpha Centauri B. They orbit each other closely, like 2 dancers holding hands and turning around a shared centre. They are both ordinary, healthy, middle-aged stars, not so different from our sun. One of them, the A star, is a little brighter and a little larger. The other, the B star, is a little smaller and a little cooler, with a more orange colour. Together they make up the bright point you would see. These two stars do not sit still beside each other. They swing around their common centre on a long stretched path that takes about 80 years to complete one full loop. As they go, the gap between them changes a great deal. At their closest, they come within about 11 times the distance between Earth and the Sun. At their farthest, they spread out to more than 30 times that distance. So the system breathes, slowly, over a human lifetime, drawing in and stretching out. The third star is the odd one. It is called Proxima Centauri. It is a red dwarf, which means it is small, cool and dim, glowing a deep red. It is far less bright than its two companions, so faint that you cannot see it without a telescope, even though it is right there in the same system. Proxima sits much farther out from the central pair, looping around them on an enormous slow orbit that takes hundreds of thousands of years. And here is a lovely detail. Proxima Centauri, the faint little one, is actually the closest single star to our Sun. Its name even says so. Proxima means nearest. It edges out its brighter siblings by a small margin, sitting just slightly nearer to us. So the dimmest member of the family wears the crown for being our true nearest neighbour. This 3-star arrangement matters for our story, and we will keep coming back to it. A system with more than one star is a crowded, restless place. The pull of gravity is not coming from one steady source, but from several, all tugging in different directions as they move. For a planet trying to form and survive there, that is a hard environment. Things can get flung out. Orbits can get stirred up. So when we ask whether Alpha Centauri has planets, we're not asking a simple question. We're asking whether a world can take hold in a place with 2 suns close by and a third in the distance. For a long time, many scientists thought the answer near the 2 bright stars might be no. The chaos seemed too much. The faint red dwarf gave us our first real answer though. Proxima Centauri, it turned out, does have planets. We will get to those. They told us that this system is not empty. They opened the door, but the bright pair, the A and B stars, stayed quiet far longer. They are the harder targets, the ones drowned in their own light. The new discovery is about one of them. So as we go forward, keep the family in mind. 2 bright stars close and circling, 1 faint red star far away. And somewhere in that crowded dance, perhaps, a planet. Let me introduce the star at the centre of this story properly. Its name is Alpha Centauri A, and of all the stars we have ever studied, it is one of the most familiar, because it is almost a copy of our own Sun. Astronomers sort stars by their colour, their temperature and their size. Our Sun falls into a category often called a yellow dwarf, which is a slightly misleading name, because the Sun is not really yellow and not really small. It is a steady, middle-sized, middle-aged star. Alpha Centauri A sits in that same category. It has nearly the same mass as the Sun, just a touch more. It has nearly the same temperature. It shines with nearly the same light. If you placed it where the Sun is, you would barely notice the difference. This is why scientists call it a solar twin. It is the nearest star to us that is truly like our own. That makes it precious. When we study the Sun, we cannot step back and see it from the outside. We are too close. We are inside its glare. But a Sun-like star a few light years away gives us a chance to see what a star like ours looks like from a distance, and to ask the question that follows naturally. If our Sun has a family of planets, might this one too? Alpha Centauri A is also old, in the comfortable way that the Sun is old. It has been shining steadily for billions of years, around the same length of time as the Sun. It is not a young, violent star, and it is not a dying one. It is in the long, calm middle of its life. That steadiness matters. A calm star is a friendlier place for planets, and a friendlier place for anything that might live on them. The companion star, Alpha Centauri B, is worth a word here too, because the two are always together. The B star is smaller and cooler, more orange in tone, the kind of star astronomers call an orange dwarf. It is a perfectly good star in its own right, just a step down in size and heat from its brighter sibling. The two of them together are what makes the bright point in our sky. But the brightness of these two stars side by side is exactly the trouble. Alpha Centauri A is in fact the third brightest star in our entire night sky. Only two stars appear brighter from Earth. That brightness is wonderful if you simply want to admire it. It is a nightmare if you want to find a faint planet sitting right next to it. Think about what a planet is. It does not make its own light, or almost none. It only reflects and re-radiates the light of its star. Next to a star as bright as this one, a planet is a vanishingly faint speck, perhaps tens of thousands of times dimmer. Picking that speck out of the surrounding glare is one of the hardest things in all of observational astronomy. So we have a beautiful target and a terrible problem at once. A star so like our Sun that it begs to be searched for planets, and a star so bright that searching it has defeated nearly every attempt. For decades, that tension defined the hunt. We wanted more than almost anywhere to find a world here. And here, more than almost anywhere, the glare said no. Keep that tension in mind. It is the reason this discovery took so long, and the reason it took such an extraordinary telescope to finally see past the light. Step outside for a moment in your mind and go south. If you have only ever lived in the northern half of the world, you have likely never seen this star with your own eyes. Alpha Centauri sits low in the southern sky, and from much of the north, it never rises above the horizon. To see it, you have to travel toward the equator and beyond. But for people across the southern half of the Earth, it is an old friend. It hangs near a famous little pattern of stars called the Southern Cross, and it acts as a kind of pointer toward it. Two bright stars stand side by side there, and the brighter of the pair is our Alpha Centauri. Sailors and travellers in the southern oceans have used these stars to find their way for a very long time. The star has old names too, carried down through different cultures. One of them is Ridgel Centaurus, which comes from an Arabic phrase meaning the foot of the centaur, because the star marks the foot of the figure in the constellation Centaurus, the centaur. Another, older name is Ptolemy. These names remind us that long before anyone knew this was a triple system of sun-like stars, people were already watching it, naming it, weaving it into their sky stories. What they were watching, without knowing it, was the combined glow of at least two stars blended into one. The human eye cannot separate Alpha Centauri A and B. They're too close together from our point of view, and the light simply merges. It took telescopes to split them apart and reveal that the single foot of the centaur was really a pair of suns turning around each other. This is a good moment to picture the scene honestly. From Earth, Alpha Centauri is just a point. A bright one, yes, the third brightest in the night, but still only a point of light like every other star. There is no disk to see, no surface, no colour you could be sure of with the naked eye. All the richness we have been describing, the two suns, the orbit, the faint red dwarf, the possible planet, is hidden inside that single dot. That is the strange truth about astronomy. Almost everything we know about distant stars we have pulled out of points of light. We cannot fly there, we cannot touch them. We gather their light, spread it out, measure it, and from those measurements we reconstruct whole worlds. A star's colour tells us its temperature. The way its light shifts tells us how it moves. The faint companions beside it, if we can catch them, tell us about planets. So when astronomers wanted to search Alpha Centauri for planets, they were working with that same point of light. They had to take the blended glow of two brilliant stars and find, hidden somewhere in it, a signal far fainter than the stars themselves. It is a little like standing on one shore and trying to hear a whisper from the opposite bank of a wide, roaring river. And before we get to how they finally caught that whisper, it is worth pausing on why anyone tried so hard. There are billions of stars. Astronomers cannot study them all in this kind of detail. Why pour so much effort into this one point in the southern sky? The answer comes down to a single word that we have already touched, and that we will turn over carefully next: closeness. Of all the places we might look for another world, this one is nearest to home. Let us slow down on this idea of nearness, because it is the reason Alpha Centauri sits at the very top of so many wish lists in astronomy. We have now found a great many planets around other stars. The count runs into the thousands, with many thousands more waiting to be confirmed. Most of them are very far away, hundreds or even thousands of light years off. We know they exist, and we know a little about their size and their orbit, but they are too distant for us to study in any detail. They are dots inferred from other dots. A planet at Alpha Centauri would be different. It would be, by a wide margin, the closest planet to us around a star like our Sun. And closeness, in astronomy, is everything. The nearer a thing is, the more of its light reaches us, and the more light we have, the more we can learn. With enough light, we can begin to ask deep questions. What is the planet made of? Does it have an atmosphere? What is in that atmosphere? Is there anything there that hints at life? For a faraway planet, those questions are mostly out of reach. For a planet next door, they start to become possible. So a world at Alpha Centauri would not just be one more entry on a long list. It would be a touchstone, a nearby example we could return to again and again, with telescope after telescope, learning more each time. It would be the place where we test our best tools and our best ideas. There is also something simpler at work, something human. This is the nearest system. If we ever, in some distant future, sent a probe to another star, this is almost certainly where we would aim it first. It is the natural target for any dream of reaching beyond our own sun. A confirmed planet there would give that dream a destination. Not just a star to fly toward, but a world. That is also why the search here has been so frustrating for so long. We could see the perfect target. We knew it was close. We knew at least one of its stars was nearly a twin of our own. And yet, for the two bright stars, every attempt to find a planet ran into the same wall of glare. The closeness that made the prize so valuable did nothing to make it easier to grasp. The stars were near, but they were also blinding. This is the point in the story. If you're enjoying this slow walk through the nearest stars, to gently subscribe so the next quiet journey finds its way to you. So the value was clear, and the difficulty was clear. What was missing was a tool sharp enough to cut through the light. For years, the instruments simply were not good enough. The faint signal of a planet beside Alpha Centauri A was lost in the brilliance of the star, and there was no way around it. That is what makes the recent chapter so striking. A new telescope arrived, built with a special ability to block the light of a star and reveal what hides beside it. And one of the first hard targets it took on was this very system, the most wanted, most difficult prize in the nearby sky. Before we meet that telescope, though, we should give credit to the earlier searches and to the one place in this system where the hunt had already, quietly, succeeded. Because the bright stars were not the first to give up a planet. The faint red dwarf got there first. The search for planets around Alpha Centauri did not begin with the new telescope. It is much older than that. For most of the past century, finding planets around any other star was simply impossible. The tools were not there, so the dream lived mostly in imagination, in stories, and in hope. Then, slowly, the tools caught up. In the final years of the 20th century, astronomers confirmed the first planets orbiting ordinary stars beyond the Sun. It was a turning point. Suddenly the question was no longer whether other worlds existed. We knew they did. The question became how many, and where, and whether any were like ours. And almost as soon as that door opened, people looked toward the nearest system and wondered what it held. The trouble was that the early methods for finding planets did not suit Alpha Centauri well. One of the main techniques watches a star for a tiny regular wobble. A planet's gravity tugs on its star, and that tug shifts the star's light back and forth by a minute amount. By measuring the shift, astronomers can infer a planet they cannot see. It is a powerful method, and it has found many worlds. But at Alpha Centauri, this method ran into the two-star problem. With the A and B stars both close together and both moving, their light blended and shifted in complicated ways. Teasing out the faint extra wobble of a possible planet on top of the large motions of the stars themselves was extremely hard. Over the years, more than one team announced a possible planet here using this approach, and more than one announcement later faded under closer scrutiny. The signals were too small and too tangled to trust. Another technique watches for a planet passing directly in front of its star, blocking a tiny sliver of light. This works beautifully for some systems, but it only works if the planet's orbit happens to line up edge-on from our point of view. For Alpha Centauri, the geometry was not kind, and the steady search for such crossings did not turn up a clear world around the bright pair. So decade after decade, the nearest sun-like stars held their silence. Each new instrument raised hopes. Each careful look ended for the A and B stars without a confirmed planet. It was not for lack of trying. Some of the finest astronomers in the world kept returning to this system, drawn by the same pull we have been describing. It was simply that the stars were too bright, too close together, and too restless for the methods of the time. Yet the failures were not wasted. Each one taught the next team something. Each ruled out certain kinds of planets, certain orbits, certain sizes. Bit by bit, the picture sharpened, not by finding a world, but by narrowing down where one could and could not be. The empty results were themselves a kind of map, and through all of it, the conviction held that there was probably something to find. Planets, we were learning, are common. Most stars have them. It would have been strange for the nearest sun-like stars to have none at all. The absence of a detection was not proof of an absence of planets. It was, more likely, proof that our eyes were not yet sharp enough. What was needed was a different way of looking. Not the wobble, not the crossing, but a direct attempt to actually see the faint glow of a planet next to its star by blocking the star's light. That method was coming, and the first clear hint that it might work at Alpha Centauri came from the ground, from a clever experiment a few years before the new telescope ever flew. While the two bright stars kept their silence, the faint third star quietly broke it. Proxima Centauri, the dim red dwarf far out at the edge of the system, turned out to have planets of its own, and one of them became famous. In the middle of the last decade, astronomers announced that Proxima Centauri had a planet roughly the size of Earth, moving around it in the right place to allow liquid water. They called it Proxima b. The news travelled around the world. The nearest star to the Sun had an Earth-sized world in what we call the habitable zone, the band around a star where temperatures might allow water to stay liquid on a surface. It was, and still is, the closest planet of its kind that we know. It is worth understanding why Proxima gave up its planet when its bright siblings would not. The reason comes down to size and brightness. Proxima is a small, faint star. A planet tugging on a small star produces a relatively larger wobble, easier to measure. And because the star is dim, its light does not overwhelm the search the way the glare of the bright pair does. The very faintness that hides Proxima from our naked eye made it, in some ways, an easier place to find planets. Later work suggested Proxima may have more than one planet. There are signs of at least two others, including a small one orbiting very close to the star and a larger one farther out. The picture is still being refined, but it is clear enough that Proxima Centauri is not a lonely star. It is a small star with a small family of worlds. Now Proxima b and its siblings are exciting, but they come with hard questions. Proxima is a red dwarf, and red dwarfs are restless in their youth and even in maturity. They tend to throw off powerful flares, sudden bursts of radiation that can lash any nearby planet. A world in the habitable zone of a red dwarf sits close to the star because the star is cool, and that closeness means it takes the full force of those flares. Whether life could survive such conditions is genuinely uncertain. Scientists debate it honestly, and there is no settled answer. So Proxima's planets are tantalizing but troubled. They are close, they are real, and at least one sits in the right temperature zone. Yet the star they orbit may be a difficult parent. That is exactly the kind of place where it helps to say plainly that we do not yet know. The wonder here is real, but so is the uncertainty. What Proxima's worlds did, above all, was prove a point. they show that the nearest star system is not empty. Planets do form and survive here, at least around the faint red dwarf. That made the silence of the two bright stars even more striking. If the dim little member of the family had planets, surely the two sun-like stars might as well. The absence of a detection at A and B started to look more and more like a limit of our tools, not a true emptiness, and this is where the brightest star, Alpha Centauri A, comes back into focus. It is the solar twin. It is the one most like our Sun. A planet there would matter even more than a planet at Proxima, because it would circle a star almost identical to ours, in the kind of orbit where our own Earth sits. The prize was always the bright star. The question was only how to see past its light. The first real hint that we might came not from space, but from a mountaintop. To understand the discovery, you have to understand the obstacle, and the obstacle is light. Specifically, it is the overwhelming light of the star itself, sitting right where you want to look. Picture the problem this way. Imagine a powerful searchlight pointed straight at you from across a stadium. Now imagine that, somewhere very close to that searchlight, a single firefly is glowing. Your task is to spot the firefly. The searchlight is so bright that it floods your eyes, and the firefly's tiny light vanishes into the glare. You know it is there, you simply cannot see it. That is, in essence, the challenge of imaging a planet next to its star. A star like Alpha Centauri A is not just brighter than its planet by a little. It is brighter by something like 10,000 times or more, in the kind of light the telescope was using. The planet's faint glow sits right beside an object tens of thousands of times more brilliant. To see the planet, you have to somehow remove the star's light while keeping the planet's. It is a delicate, almost surgical task. There is a tool built for exactly this called a coronagraph. The idea is simple to describe and very hard to perfect. Inside the telescope you place a small mask, a kind of carefully shaped block, right over the spot where the star's light comes to a focus. The mask blocks the bright central light of the star, the way you might raise your hand to block the sun so you can see something near it. With the star's glare suppressed, fainter objects around it can come into view. But a coronagraph is not a perfect shade. Light does not simply stop at the edge of the mask. It bends and ripples around it, leaving faint patterns of leftover starlight spread across the image. Those ripples can easily be brighter than the planet you are hunting. So blocking the star is only the first step. After that, you have to carefully understand and subtract those leftover patterns, peeling away every trace of the star until only the true faint objects remain. Now add the special difficulty of Alpha Centauri. There are two bright stars, not one, sitting close together. Even if you block the light of the A star with your mask, the B star is right there, still blazing away nearby, spilling its own light across your image. So you're not just fighting one searchlight, you're fighting two, and one of them you cannot cover. The extra glow from the companion star makes the whole task harder than it would be for a lone star. On top of that, the system moves. The stars of Alpha Centauri travel across our sky relatively quickly, compared with more distant stars, because they are so near. Over the course of careful observations, the target shifts. The instruments have to track that motion precisely, or the whole delicate measurement smears. Put it all together, and you have one of the most demanding observations imaginable. A chronograph straining to block a star, a second star refusing to be blocked, a faint planet thousands of times dimmer than either, and the whole arrangement drifting across the sky as you watch. It is no wonder that, for so long, no one could pull a clear planet out of the glare at Alpha Centauri A. To do it, you would need a telescope larger and steadier than anything before, working in just the right kind of light, with a coronagraph built to an extraordinary standard. That telescope, by the time of this story, finally existed. But before it looked, a ground-based experiment caught the very first whisper. A few years before, the new space telescope turned its eye toward Alpha Centauri. A clever experiment on the ground caught something. It was faint, it was uncertain, and at the time no one could be sure what it was. But looking back, it may have been our first glimpse of the very object this whole story is about. The experiment ran at a large telescope in the high desert of South America, where the air is thin and dry and the skies are among the clearest on Earth. The instrument was specially adapted to hunt for warm planets around the Alpha Centauri stars by working in mid-infrared light, the kind of light a warm object gives off as heat. The project even had a name that spoke to its ambition, built around the idea of searching for new Earths in the region of Alpha Centauri. This kind of search has an advantage in the infrared. A planet, especially a large warm one, glows in heat. In ordinary visible light, the planet is only a faint reflection beside a brilliant star. In the infrared, the contrast between star and planet is gentler, and a warm planet stands out a little more against its star. So an infrared search, with a coronagraph to block the starlight, had a real chance of catching a giant planet that visible light methods would miss. In the data from that campaign, around the end of the last decade, there appeared a possible signal, a faint point of light, in roughly the place where a planet might sit beside Alpha Centauri A. It was the kind of result that makes an astronomer's heart beat faster and then immediately makes them cautious. Was it a real planet? Or was it a trick of the instrument, a leftover ripple of starlight, a smudge of noise dressed up to look like a world? The honest answer at the time was that no one could say for certain. The signal was tantalizing but not solid. It never quite hardened into a confirmed discovery. It sat in that uncomfortable middle ground where many candidate planets live, too interesting to dismiss and too weak to trust. So it was noted and remembered and set aside as a maybe, a whisper, not a shout. What mattered, though, was that the whisper existed at all. It hinted that there might really be something there, a warm giant planet around the brightest star in the nearest system, and it gave future searchers a clue about where to look and what kind of object to expect. If you are hunting in the dark and someone tells you they once thought they heard a sound from a particular direction, you point your ears that way. That earlier hint would become important later, in a way that no one could have planned. When the new telescope eventually gathered its own data and ran into a deep mystery, this old, uncertain ground-based signal would be pulled back out, dusted off, and fitted into the puzzle. A measurement that on its own meant little would, in combination with new data, help build the case for a single consistent world. But that is getting ahead of the story. At the time, the whisper simply hung there, unresolved. It told us that Alpha Centauri A was worth a very hard look with the best instrument we could bring to bear. The ground had done what it could, peering through the shifting blanket of the atmosphere. To go further, the search had to leave the Earth behind, rise above the air entirely, and look from the cold, steady dark of space. That is exactly where the next instrument waited. Now the main character of this story arrives. It is the James Webb Space Telescope, the largest and most powerful telescope we have ever sent into space. It was built over many years by a partnership of space agencies, led by the American Space Agency, working together with the European and Canadian space agencies. When it finally launched and unfolded, it opened a new era in our view of the universe. To understand why it could do what earlier instruments could not, picture where it sits and how it works. The telescope does not orbit close to Earth. It travels out to a special quiet point in space, far beyond the Moon, about 1 million miles from Earth. At that point, the pull of the Earth and the Sun balance in a way that lets the telescope hold a stable position while it circles the Sun alongside our planet. It is a calm, cold, far-off perch, away from the heat and glare of home. That distance and cold are not an accident. They are the whole point. The James Webb Telescope is built to see infrared light, which is essentially heat. To detect the faint heat of distant objects, the telescope itself must be extremely cold, or its own warmth would drown out everything it tries to see. So it carries a vast sun shield, a tennis court-sized barrier that blocks the sun, the Earth and the Moon, keeping the instruments in deep, frozen shadow. Sitting far from Earth, behind that shield, the telescope grows cold enough to sense the faint warmth of worlds light years away. Its main mirror is enormous, far larger than any telescope flown before it, made of segments that unfolded in space like a flower opening. A bigger mirror gathers more light, and more light means it can see fainter things and see them more sharply. Combine a giant cold mirror, a perch in steady space above the blurring atmosphere, and a design tuned for infrared, and you have an instrument almost tailor-made for the hardest kinds of planet hunting. Think back to the obstacles we laid out. To see a planet beside Alpha Centauri A, you needed to work in the infrared, where a warm planet stands out better against its star. You needed to be above the Earth's shimmering atmosphere, which smears fine detail. You needed a coronagraph built to a very high standard to block the star's light cleanly, and you needed a telescope large and steady enough to catch a signal tens of thousands of times fainter than the star. The James Webb Telescope offered all of these at once, so it was natural that among its many tasks, astronomers would aim it at the nearest sun-like star and try the observation that had defeated everyone before. It was never going to be easy, even for this machine. The two bright stars, so close together, so quick across the sky, would push the telescope and its team to their limits. But for the first time, the tool was genuinely capable of the job. This is part of what makes the James Webb Telescope such a remarkable thing. It was not built only to look at the most distant galaxies, though it does that beautifully. It was also built to turn its gaze close to home and study the nearest worlds in detail we could never reach before. The same instrument that peers back toward the dawn of the universe can also lean in toward the star next door. And lean in it did. To make the actual attempt at Alpha Centauri, the telescope would use one particular instrument with one particular trick built into it. That instrument is where we go next. The James Webb Telescope carries several scientific instruments, each tuned to a different job. The one at the heart of this discovery is called the Mid-Infrared Instrument. Most people simply call it by its short name, MIRI. As the name says, it works in the middle range of infrared light, deeper into the heat part of the spectrum than the telescope's other tools. That choice of light is important. We said earlier that a warm planet glows in the infrared, and that the gap in brightness between a star and its planet is gentler there than in visible light. The mid-infrared, where this instrument works, is especially good for catching the warm glow of giant planets. A large planet, still holding leftover heat from its formation, shines in this range in a way that gives it a fighting chance against the brilliance of its star. So if you want to image a warm giant planet beside a sun-like star, the mid-infrared is a smart place to look, and this instrument is the tool for it. Built into the instrument is the key device for this kind of work, a coronagraph. We met the idea before. It is the small, carefully shaped mask that blocks the bright central light of a star so that fainter objects around it can be seen. The coronagraph on this instrument is among the most refined ever flown, designed to suppress a star's glare and reveal the faint companions hiding in its light. Using it, though, is far from automatic. To point the mask precisely over a star, to hold it there steadily, and to gather enough light to catch a faint planet takes great care. For most targets, the instrument's standard routines do the job. Alpha Centauri was not most targets. It was so bright, so close, and so quick across the sky that the usual approach would not work. The team had to design a special, custom sequence of observations just for this one system, a tailored plan to wring a clean measurement out of an unusually difficult target. That extra effort is worth dwelling on, because it shows how this kind of science really happens. It is not a matter of pointing a telescope and snapping a picture. It is a matter of understanding the specific quirks of a specific target, and then building a careful, clever procedure to handle them. The brightness of the two stars, their tight spacing, their rapid motion across the sky, all of it had to be planned for. The operations team essentially invented a new way of using the instrument, just to make this observation possible. It is also worth saying that the people who built this instrument had Alpha Centauri in mind from early on. When you design a tool to block starlight and find planets, the nearest Sun-like star is one of the dream targets you imagine pointing it at. So when the chance came to actually try, there was a sense of long-awaited purpose to it. The instrument had been built in part for exactly this kind of moment. The mid-infrared light, the high-grade coronagraph, the custom observing plan, and the steady cold platform of the telescope all came together for one attempt at the brightest star in the nearest system. Everything that had made this observation impossible before was finally addressed. The tool was ready. The target was chosen. The plan was set. What remained was to actually look, to gather the light, and to see whether anything faint sat hidden beside Alpha Centauri A. That first real look came on a specific occasion, and it is where the discovery truly begins. The first attempt came in the late summer of one recent year, when the telescope turned toward Alpha Centauri A and set its coronagraph to work. This was the moment the long preparation had been building toward. The custom observing plan was run. The mask was placed over the bright star. The instrument gathered the faint mid-infrared light coming from the region around it. It helps to picture what the telescope was actually trying to do in that moment. Out beyond the mask, in the area just to the side of the blocked star, the instrument was collecting every scrap of warm light it could. Somewhere in that light, if a planet existed, would be a tiny extra glow, a point far dimmer than the star, sitting at some small distance from it. The whole observation was a search for that one faint point amid a field still littered with leftover starlight. The companion star made it harder, as expected. Even with the A star's light blocked by the mask, the B star nearby kept shining, throwing its own glow across the image. So the raw picture that came back was not a clean dark field with a neat planet in it. It was a complicated scene, full of the bright leftovers of two stars, with any planet buried somewhere inside. This is the honest texture of such work. The first look does not hand you a planet. It hands you a difficult image full of starlight that has to be understood and removed. The real discovery happens afterward, in the careful processing, when the team works to subtract every trace of the stars and see what, if anything, remains. But the first look did its essential job. It gathered the data. It captured in that warm infrared light whatever was actually there around Alpha Centauri A on that occasion. Everything that followed, all the analysis and the long detective work, would be built on the light collected in this single, painstaking observation. You cannot find a planet you have not gathered the light from. This was the gathering. There is something quietly moving about that moment, if you let yourself feel it. After decades of failed attempts at the bright stars of Alpha Centauri, after all the announcements that faded and all the methods that fell short, here was the most capable telescope ever built, finally aimed at the prize, gathering exactly the kind of light most likely to reveal a giant planet. Years of design, construction and planning came down to a window of careful observation pointed at the star next door. The people involved later described how demanding it was, among the most challenging observations the instrument had attempted. The brightness, the closeness, the motion, everything that made the target hard was in full effect. That the observation worked at all was a real achievement, the payoff of the extra effort that went into designing it. And once the light was gathered, the question became the one that always follows. What was in it? You cannot answer that by glancing at the raw image. The starlight is still everywhere. The planet, if it is there, is hidden. To find it, you have to do the delicate work of peeling the starlight away, layer by layer, until the faint truth underneath is exposed. That peeling, that careful subtraction of 2 stars worth of glare, is the next step in the story. It is where a confusing image of leftover light begins to turn into something far more interesting. A single faint point that should not be there unless it is real. Gathering the light was only the beginning. The harder, slower work came afterward, in the careful removal of everything that was not the planet. This is where a confusing image, full of 2 stars worth of glare, was patiently turned into something clear enough to study. remember the central difficulty. Even with the coronagraph blocking the bright star, light does not vanish cleanly. It bends around the edges of the mask and spreads out in faint ripples and patterns across the image. And here there was a second star nearby, the companion, adding its own glow on top. So the raw picture was a tangle of leftover starlight from both stars, any one ripple of which could easily outshine a real planet. To find the planet, the team had to understand that leftover light precisely, and then subtract it. Think of it like cleaning a window so dirty you cannot see through it. You cannot just wipe once. You study exactly how the grime is spread, you remove it carefully, and only when the glass is truly clear can you see what lies beyond. Here, the grime was starlight, and removing it meant modelling, with great care, exactly how the light of each star spread across the image, and then taking that pattern away. This kind of subtraction is one of the core arts of modern planet imaging. You build a careful picture of what the starlight alone should look like, with no planet present, and you remove it from your data. Whatever is left over, after the stars are gone, are the candidates. If a faint point of light remains standing in the cleaned image, in a place where no leftover starlight should be, then you may have found something real. The presence of the second star made this delicate work much harder. With two bright sources instead of one, the leftover patterns were more complex and there was more glow to account for and remove. The team had to subtract the light of both stars, not one, and do it cleanly enough that a faint planet thousands of times dimmer would not be lost in the imperfections of the process. It is worth pausing to honour how careful this has to be. When you are subtracting something tens of thousands of times brighter than the thing you want to keep, even a small error in the subtraction can create a fake signal or erase a real one. A leftover ripple, not quite removed, can masquerade as a planet. A real planet, slightly over-subtracted, can disappear. So the work demands not just skill, but deep caution, and a constant questioning of whether any faint point that emerges is truly a world or merely a flaw. This caution is exactly why scientists are so careful with the word they use for what they found. They do not rush to say planet. They say candidate, and they keep testing. Every faint point that survives the subtraction has to be challenged. Could it be an artifact of the process? Could it be a background object, some distant thing that just happens to lie in the same direction? Only after such questions are weighed does a faint point earn serious attention. In this case, after the starlight was peeled away, something did remain. In the cleaned mid-infrared image, in the region beside Alpha Centauri A, there sat a faint point of light. It was far dimmer than the star, sitting a certain distance out from it, exactly the kind of object the search had been hoping for. It was not proof of a planet. But it was the thing that, if real, a planet would look like, and that faint point is what we examine next. So, after all the gathering and all the subtracting, what was actually there? In the cleaned image beside Alpha Centauri A sat a single faint point of light. Let us look closely at what that point was and was not. First, its brightness, or rather its faintness. The point was extraordinarily dim compared with the star. It glowed at something like 10,000 times fainter than Alpha Centauri A itself, perhaps even fainter than that. That is the scale of the challenge we have been describing made real. The thing they found was a whisper next to a roar, a spark beside a furnace. That it could be picked out at all is a measure of how good the telescope and the analysis were. Second, its position. The point did not sit on top of the star. It sat off to one side, separated from it by a real distance. When astronomers translate that apparent gap into a true distance at the system, it works out to roughly twice the distance between the Earth and our Sun. So if this is a planet, it orbits its star a bit farther out than the Earth orbits ours, in the broad neighbourhood where, in our own system, you would find the inner edge of the warmer giant planets. That distance is a meaningful clue. It places the object in an interesting zone, not hugging the star and not far out in the cold. It is the kind of separation where a substantial planet could plausibly sit. and the fact that it appeared at a particular spot rather than smeared across the image is part of what makes it look like a real, compact object rather than a spread-out artifact. Now, the honest caveats. A single faint point in a single observation is not by itself a confirmed planet. It could in principle be several other things. It could be a flaw left over from the imperfect subtraction of all that starlight. It could be a distant background object, something far behind the star that happens to lie in the same line of sight. These possibilities have to be taken seriously, and they were. The team weighed them carefully. The brightness and colour of the point, the way it appeared in the mid-infrared, its position relative to the star, all of these were consistent with what a warm giant planet should look like, and harder to explain as a mere artifact or a chance background object. The evidence pointed toward the exciting interpretation. It did not prove it beyond all doubt, but it leaned that way. There is a particular thrill in this kind of result that is worth naming gently. For the first time, looking at the nearest sun-like star, there was a faint point of light that behaved the way a real planet should. Not a wobble inferred from shifting starlight, not a dip as something crossed the star, an actual point of light sitting beside the star that might be the glow of the planet itself, direct, in a sense you could almost picture. Of course, one observation, however promising, is only one observation. Science does not rest on a single image. The natural next step was to look again, to see if the faint point was still there, to watch it move as a real planet should as it travels along its orbit. So the telescope was pointed back at Alpha Centauri A on later occasions to confirm the find. And here the story takes its strangest turn, because when they looked again, the faint point was gone. Before we follow the twist of the vanishing point, let us stay a moment with what the team believed they were looking at. From that single faint dot combined with everything they knew, a first rough portrait of the object began to form. It is worth picturing, because it is a strange and beautiful world if it is real. Start with its mass. The brightness of the point in the mid-infrared, together with reasonable assumptions about its age and makeup, pointed to a large planet, roughly the mass of Saturn. Saturn, in our own system, is the second largest planet, a great ball of gas with its famous rings. So the object beside Alpha Centauri A would be a gas giant, a vast world made mostly of gas, with no solid surface to stand on. Not a rocky world like Earth, but a giant like the outer planets of our own family. That single fact already tells us something important. Whatever this object is, it is not a place where life as we know it could live on a surface, because it has no surface to live on. It is a giant ball of gas. So even though, as we'll see, its orbit places it in an interesting temperature zone, the planet itself is not a candidate for life. It is a different kind of marvel, a nearby giant rather than a nearby Earth. Next, its distance from the star. We said the point sat roughly twice the Earth-Sun distance out from Alpha Centauri A. Later analysis suggested its orbit is not a neat circle, but a stretched elliptical loop, swinging closer to the star at times and farther at others, ranging somewhere between about 1 and 2 times the Earth-Sun distance over the course of its path. So it does not keep a fixed distance, it moves in and out as it circles. That stretched orbit matters for several reasons, and we will come to them. For now, simply hold the picture. A Saturn-sized ball of gas, looping around a sun-like star on an oval path, sometimes about as far out as the Earth is from the Sun, sometimes about twice as far. Then there is its warmth. Because it sits relatively close to a sun-like star, the planet would be warmed by the light of its star much as our own giant planets are warmed, but more so, being nearer. Early on, its temperature was compared to that of Saturn, but a closer look suggested it is considerably warmer than Saturn, more than twice as warm in fact. So it is a warm gas giant, glowing gently with its own heat and bathed in the light of its star, and its age. Because Alpha Centauri A is about the same age as our Sun, billions of years old, any planet around it is likely old too. So this would be a mature giant, not a young, hot, freshly formed world, but one that has settled into a long, steady existence, much as our own giant planets have. Put the portrait together and you have something remarkable. A Saturn mass gas giant, warm, mature, on an elliptical orbit around the nearest sun-like star, sitting at a distance broadly comparable to the inner part of our own planetary system. The closest such world we could ever hope to study, if it is real. That last phrase is the heart of what comes next, because the careful, exciting portrait we have just drawn was built largely on one observation, and when the team went back for more, the object that anchored the whole picture refused to show itself again. Here is where the story turns from a discovery into a mystery. Having found a promising faint point of light beside Alpha Centauri A, the team did the right and obvious thing. They looked again. Twice more on 2 later occasions, the telescope was pointed back at the same star to confirm the find and to watch the planet move. Both times, the point was gone. Imagine the feeling. You make one of the most difficult observations in astronomy. You find, after careful work, a faint object exactly where a planet might be, with exactly the brightness a planet should have. You announce nothing yet because you are careful. You go back to confirm, and the object is not there. Not in the second look, not in the third. The very thing that made the discovery seem real has vanished from the image. This is the kind of result that could sink a discovery entirely. After all, if a faint point appears once and never again, the simplest explanation might be that it was never real, that it was an artifact of the difficult subtraction, a ghost of leftover starlight that fooled the eye. 2 clean non-detections on top of 1 detection do not at first sound like the recipe for announcing a planet. They sound like a warning that the first result was a mistake. The team felt the weight of this. They even described it, with some humour, as the case of a disappearing planet. It was a genuine puzzle. Was the object real and somehow hidden in the later looks, or was it never there at all? Everything depended on answering that question honestly. Now, there is a crucial idea that rescues the situation, and it comes back to the shape of the orbit. Remember that the planet, if real, moves on a stretched elliptical path around the star, swinging in and out. A planet on such an orbit does not stay put in our view. As it travels, it changes its position relative to the star as we see it. At some points along its path, it would appear well separated from the star, out where the telescope's mass could reveal it. At other points, it would swing around so that, from our line of sight, it passes nearly in front of or behind the star, lost in the very glare the coronagraph is fighting. So here is the possibility that turns the mystery around. What if, on the first occasion, the planet happened to be at a point in its orbit where it stood clear of the star and could be seen? And what if, on the 2 later occasions, it had moved along its orbit to a position too close to the star to be picked out, swallowed by the glare? Then the non-detections would not mean the planet was absent. They would mean the planet was simply, temporarily out of view, hidden behind or beside its star from our point of view. That is a tidy story, but you cannot just assert it. You have to test it. Is there really a sensible orbit, a real path obeying the laws of gravity, that would put the planet in view on the first occasion and out of view on the other 2? If such orbits exist, and if they are the kind of orbit a planet could actually hold in this 2-star system, then the disappearing act makes sense, and the planet survives as a real candidate. Answering that question is a beautiful piece of detective work, and to do it, the team turned the problem over to a vast number of imagined orbits, simulated by computer, to see which ones could explain everything they had seen and not seen. To solve the mystery of the disappearing point of light, the team did something elegant. They could not watch the planet travel its whole orbit, since they only had a few glimpses. So instead, they let a computer imagine the orbits for them, vast numbers of them, and asked which ones fit all the facts. The idea works like this. Suppose there really is a planet around Alpha Centauri A. It must be on some orbit, some particular path around the star. They did not know which path, so they generated an enormous number of possible orbits, millions of them, each a different shape and tilt and size, each a candidate for the planet's true path. For every one of those imagined orbits, they could ask a precise question. If the planet were on this orbit, where would it appear, from our point of view, on each of the dates the telescope looked? Then they checked each imagined orbit against what was actually seen. The planet had appeared on the first occasion, so a valid orbit had to place the planet in view, well clear of the star, on that date. The planet had not appeared on the two later occasions, so a valid orbit also had to place the planet out of view, too close to the star to be seen, on those dates. Any imagined orbit that got all of this right was a possible true orbit for the planet. Any that failed was thrown out. There was one more test, and it is a deep one. The orbit had to be stable. Remember, this is a two-star system with the companion star nearby exerting its own pull. Not every path is allowed in such a place. Some orbits would be torn apart by the gravity of the second star, flinging the planet out of the system over time. A real planet must be on an orbit that can survive the constant tug of the companion. So the team kept only those imagined orbits that would remain stable in the presence of the second star, the ones a planet could actually hold for the long term. They also brought in the old whisper from the ground-based search years before, that earlier uncertain hint of a point of light beside Alpha Centauri A. They folded that into the analysis too, treating it as another data point, another moment when the planet may have been seen. A valid orbit, ideally, should be consistent with that earlier sighting as well. When they put it all together, the result was reassuring. There were indeed orbits, stable, sensible paths obeying gravity that fit everything. In fact, they found that for a large share of the stable orbits consistent with the first detection, the planet would have been too close to the star to see on the two later dates. In other words, a non-detection on those occasions was not surprising at all. It was exactly what many of the allowed orbits predicted. The disappearing planet was not a contradiction. It was a natural consequence of an elliptical orbit seen at the wrong moments. This is the part of the work that turned a worrying mystery into a strengthened case. The vanishing of the point of light, which at first seemed to undermine the discovery, instead fit neatly into a coherent picture. One detection, two non-detections, and an old ground-based hint could all be explained by a single planet on a single kind of orbit, stable in its two-star home. From these surviving orbits, the team could finally describe the planet's likely path in real terms, its loop, its timing, its shape. That reconstructed orbit, and what it tells us, is where the next part of the journey begins. Out of those millions of imagined orbits, a real shape emerged for the planet's likely path. It is worth drawing it slowly, because the shape of the orbit explains nearly everything strange about this discovery. The path is not a circle, it is an ellipse, a stretched oval. The planet does not hold a steady distance from its star. Instead, it swings inward and then back outward as it travels, the way a comet does in our own system, though far more gently. At its nearest, it comes into about the distance the Earth sits from our Sun. At its farthest, it drifts out to roughly twice that distance. So over the course of one loop, the gap between planet and star grows and shrinks by a real amount. This elliptical shape is the key to the disappearing act. On a stretched orbit, the planet spends part of its time well separated from the star, out where the telescope's mask can reveal it, and part of its time swung around close, where it vanishes into the glare. Catch it at the right moment and you see it. Catch it at the wrong moment and you do not. That is exactly the pattern the observation showed. Now, how long does one full loop take? The reconstructed orbit suggests the planet circles its star somewhere in the range of 1.5 years to a few years to complete a single trip. In other words, its year is not so different in length from a couple of our own. That feels almost familiar. We are not talking about a planet that takes centuries to circle, far out in the cold, nor one that whips around in days hugging the star. It moves on a human-scaled rhythm, a year measured in a handful of our years. Tie that to something you can picture. In our own system, the Earth takes 1 year to circle the Sun, and Mars takes a little under 2. This planet, on its stretched path around a sun-like star, completes its loop on a timescale in that same broad range. So if you stood on a moon of this giant and watched its sun cross the sky, the great cycle of its year would not be wildly unlike the cycles we know. It would simply belong to another star. The tilt of the orbit matters too. The path is not lined up flat to our view. It is tilted, so that as the planet travels, it moves not just side to side but also seems to pass nearer to or farther from the star from our vantage point. This tilt, combined with the stretch of the ellipse, is what carries the planet in and out of view across the different observations. The geometry of how we happen to see the orbit, from our particular spot 4 light-years away, decides whether the planet is visible on any given night. It is a humbling thought. Whether we can see this world at all depends not only on where it is in its orbit, but on the accident of our viewing angle. Shift our position, and the pattern of appearances and disappearances would change. We are watching a distant clock, and our line of sight only lets us read certain hours of its face. From this reconstructed ellipse, then, the team could finally speak about the planet's real motion, not just a single frozen point. A Saturn-massed giant swinging between about 1 and 2 times the Earth-Sun distance, completing its loop in a small number of years, tilted to our view in just the way that explains everything we saw and did not see. But an orbit in a 2-star system is never simple. The companion star is always pulling. Whether such a path can truly last is the next question. A planet that lasts has to survive its neighbourhood, and this planet's neighbourhood is a difficult one. Alpha Centauri A is not alone. Its companion, Alpha Centauri B, circles close by on that 80-year loop we described, swinging in to about 11 times the Earth-Sun distance at its nearest. So our planet, orbiting the A star at 1 to 2 times the Earth-Sun distance, has a whole second sun sweeping past not so far beyond it. That is a genuine threat. The gravity of a passing star can stir a planet's orbit, stretch it, tilt it, and in the worst cases fling the planet right out of the system into the dark between the stars. Many possible orbits around Alpha Centauri simply would not survive. A planet placed too far out, too near the path of the companion, would be torn loose over time. So not every orbit is allowed. The system itself sets the rules. This is why the team insisted that any orbit they accepted for the planet had to be stable. It had to be a path the planet could hold not just for a year or a century, but for the long ages of the system's life, billions of years, without being thrown out by the companion's pull. They tested their imagined orbits against this requirement and kept only the survivors. What they found is reassuring and makes physical sense. There is a safe zone close to each of the 2 bright stars, a region near enough to its own star that the star's grip wins out over the disturbing tug of the companion. A planet orbiting snugly around Alpha Centauri A at 1 to 2 times the Earth-Sun distance sits comfortably within that safe zone. It is close enough to its own star to be held firmly, and far enough inside the danger line that the companion cannot wrench it away. Think of it like 2 spinning tops set near each other on a table. Close to each top, small objects can circle safely, caught in that top zone spin, but out in the middle ground between them, things get knocked about and cannot settle. A planet hugging one of the 2 stars is in the calm inner region. A planet trying to orbit far out, between or around both stars, would be in the chaotic middle. Our candidate is in the calm inner region of the A star, which is exactly where it should be to last. So the orbit is not only consistent with what we saw and did not see, it is also a path that a real planet could genuinely hold for the lifetime of the system. That matters enormously. It means the planet is not some fragile, doomed thing that happened to drift by. It means it could be a permanent member of the system, settled into a stable loop around its star, weathering the regular passes of the companion for billions of years. And that, in turn, raises one of the deepest questions in this whole story. How did such a planet come to be there at all? Forming a planet is hard enough around a single quiet star. Forming and keeping one in a place where a second star sweeps past every few decades is a real puzzle. The stability tells us a planet can survive here once it exists. It does not tell us how it got here in the first place. We will come to that puzzle of formation, because it is one of the most interesting things this discovery touches. But first, let us gather the threads of the detection itself, because the case for this planet does not rest on one image alone. It rests on weaving several glimpses across the years into one consistent world. The strength of this discovery comes not from a single picture, but from how several separate glimpses, scattered across years, can be woven into one consistent story. Let us lay them out together, because seeing them side by side is what makes the case compelling. The first glimpse came from the ground, years before the space telescope looked. That was the uncertain signal from the infrared search at the large telescope in the southern desert, a faint possible point beside Alpha Centauri A that nobody could confirm at the time. On its own, it meant little. It was a maybe set aside. The second glimpse was the strong one, the detection by the space telescope's mid-infrared instrument in late summer of one recent year. That was the clean faint point, 10,000 times dimmer than the star, sitting about twice the Earth-Sun distance out. That was the observation that started this whole story. Then came the two non-glimpses, the looks on two later occasions when the telescope returned and found nothing. Empty images, the planet not there. 4 moments then, one old uncertain hint, one clear detection, and 2 clean absences. Taken separately, they seem to argue with each other. A hint, a sighting, and then nothing, twice. It would be easy to read that as a story of a signal that was never real. But here is the quiet power of the orbit analysis. When the team asked whether a single planet on a single stable elliptical orbit could account for all 4 moments at once, the answer was yes. There are real orbits on which the planet would have been visible during the old ground-based search and during the space telescope's detection, and hidden, swung too close to the star during the 2 later looks. One world, one path, explaining the hint, the sighting, and both absences together. That is a far stronger thing than any single observation. A lone faint point in one image is easy to doubt, but a faint point that appears in 2 independent observations years apart from 2 different telescopes at positions that fit the same orbit and that is absent exactly when that orbit predicts it should be absent, is much harder to dismiss as noise or accident. The pieces lock together. The story holds. This is how careful science often builds confidence, not from one dramatic result, but from the way many imperfect pieces fit a single explanation. Each glimpse alone is weak. Together, arranged along one orbit, they reinforce each other. The whole becomes far sturdier than any of its parts. It is worth being honest about what this does and does not prove. It does not make the planet certain. 2 of the 4 moments are absences, and the old ground-based hint was always faint. The case rests on a model, on the claim that one orbit ties everything together. That is strong evidence, the strongest yet for a planet around this star, but it is not the final word. The scientists themselves are careful to call it a candidate, not a confirmed world. Still, after decades of silence from the bright stars of Alpha Centauri, this is a remarkable place to have arrived. A coherent picture of a single giant planet, drawn from glimpses across years and instruments, all consistent with one stable orbit around the nearest sun-like star. The threads, tangled at first, weave into one world, and that world sits in a particular and interesting place around its star, a place we often talk about when we dream of life. Whether that matters here, for a giant ball of gas, is a question worth handling with care. There is a phrase that comes up again and again when we talk about planets and the search for life. It is the habitable zone, and this planet, by an interesting coincidence, sits within it. So we should understand what that means, and just as importantly what it does not mean here. The habitable zone is the band of distances around a star where the temperature would allow liquid water to exist on the surface of a world, if that world had a surface and the right kind of atmosphere. Too close to the star, and water boils away. Too far and it freezes solid. In between lies the comfortable band, sometimes called the zone where water could stay liquid. For a sun-like star, that band sits at a distance broadly like the one Earth occupies around our Sun. Our candidate planet orbiting Alpha Centauri A at about 1 to 2 times the Earth-Sun distance falls within that comfortable band. If you only heard that a planet around the nearest sun-like star sits in the habitable zone, you might leap straight to thoughts of another Earth, of oceans and maybe life. It is a natural leap. But here it would be the wrong one, and the reason is what the planet is made of. This world is a gas giant, roughly the mass of Saturn. It is not a rocky planet with a solid surface and a thin atmosphere above it. It is a vast ball of gas, with no ground to stand on, no surface for oceans to pool on, no place for the familiar picture of a habitable world. Being in the habitable zone tells you about temperature, about the gentle warmth of the orbit. It does not turn a gas giant into a place life as we know it could take hold. So we have to hold 2 true things at once, calmly. The planet is in the habitable zone in terms of its distance and warmth, and the planet is not in itself habitable because it is a giant ball of gas. Both are true. The interesting part is simply that a giant planet happens to sit at the comfortable distance, rather than far out in the cold where the giants in our own system live. That is itself a little unusual and a little wonderful. In our solar system, the giant planets are all far from the Sun, out in the chill beyond Mars. The idea of a Saturn-sized world sitting in the warm zone, where in our system you would find rocky planets, is a different arrangement from our own. It is a reminder that other systems can lay out their planets in ways that do not match the pattern we grew up with. It also gives us pause about that warm zone around Alpha Centauri A. A giant planet sitting there raises questions about what else could be in that region. Could smaller rocky worlds also exist nearby, sharing the comfortable band? The presence of a giant does not rule them out, but it shapes the possibilities, since a large planet's gravity influences everything around it. These are open questions, and the honest answer is that we do not yet know. For now, the picture is a warm giant in a comfortable orbit, beautiful and strange, but not a home for surface life. And yet, when we have a giant planet in a temperate zone, scientists often raise one more gentle possibility, not about the planet itself, but about what might circle it. Around our own giants, after all, there are moons. Some of them are remarkable. That thought leads us naturally to the next quiet idea. A gas giant has no surface, and so it cannot host life as we know it, but a gas giant is rarely alone. In our own system, the great planets are each surrounded by families of moons, some of them whole worlds in their own right. So when we find a giant planet in a temperate orbit, a quiet question follows. What about its moons? Look at our own giant planets for the idea. Jupiter and Saturn each hold dozens of moons. Some are tiny chips of rock and ice, but some are large, complex worlds. Saturn's moon Titan has a thick atmosphere and lakes of liquid, though of a frigid, exotic kind. Jupiter's moon, Europa, and Saturn's moon, Enceladus, are thought to hide oceans of liquid water beneath their icy shells, kept warm not by the distant sun but by the flexing pull of their giant planet's gravity. These moons are among the most promising places to search for life within our own solar system. Now carry that idea to Alpha Centauri A. If there is a Saturn-mass giant sitting in the warm, habitable zone of a sun-like star, then any large moons it might have would sit in that warm zone too. A moon there would not have to rely on hidden internal heat to stay temperate. It would be bathed in the gentle warmth of a sun-like star at a comfortable distance. A reasonably large moon with the right atmosphere could in principle have liquid water on its surface, warmed from outside rather than within. This is, to be clear, a hopeful thought experiment, not a discovery. We have not seen any moon around this planet. We can barely see the planet itself, and only sometimes. A moon would be far too small and faint to detect with the tools we have now, so we are not claiming a habitable moon exists. We're noticing that the situation a giant planet in the warm zone of a sun-like star is exactly the kind of place where, if there were a large moon, it could be an interesting world. It is a lovely reversal of the usual story. We often imagine life on a planet with moons as mere companions. Here, the planet is a giant where surface life cannot live, and the interesting real estate, if any exists, would be the moons. The big world becomes the warm anchor, and a smaller world circling it becomes the possible home. Whether such moons exist around this planet is completely unknown, and we should be plain about that. Large moons are common around giant planets in our own system, but we cannot assume the same elsewhere, and we have no way yet to look. This is a possibility raised by analogy, a gentle maybe, not a measurement. It belongs in the realm of careful imagination. Still, it is the kind of imagination that keeps the search honest and alive. It reminds us that habitability can hide in unexpected places, not on the obvious large planet, but on a quiet moon beside it. And it adds one more reason to keep watching Alpha Centauri A closely in the years ahead. A confirmed giant planet there would be a doorway to a whole set of new questions, including this one. But before we get carried too far into what might circle the planet, there is a more basic puzzle to face about the planet itself. How did a giant world come to exist here at all, in a place where a second star sweeps past every few decades? Forming a planet in such a setting is no small thing. We have talked about whether the planet can survive in its two-star home. There is a harder question hiding underneath that one. Not how it survives, but how it formed in the first place. Building a giant planet is challenging even around a calm, lonely star. Building one beside a second star that sweeps past every few decades is a real puzzle. Start with how we think giant planets usually form. Around a young star, there is a broad, flat disk of gas and dust, the leftover material from the star's own birth. Within that disk, dust grains stick together into pebbles, pebbles gather into rocks, rocks build into larger bodies, and the largest of these can grow heavy enough to pull in great envelopes of gas, becoming giant planets. It is a slow process of gathering. Building up a world from the disk over a long stretch of time, it needs a stable, undisturbed disk to work in. Now add the second star. In a system like Alpha Centauri, the companion star's gravity can stir and truncate that early disk, cutting it short and churning the material within it. A disturbed disk is a harder place to quietly build a planet. The gentle gathering can be disrupted, the building blocks scattered before they have time to come together. For a long time, this made some scientists doubt that large planets could form around the individual stars of close binary systems at all. So the very existence of a giant planet around Alpha Centauri A, if confirmed, would be informative, even challenging. It would tell us that planet formation can succeed even in these restless two-star settings, that a disk around one star of a close pair can hold together long enough and gather enough material to build a world the size of Saturn. That is not something we could simply assume. It is the kind of fact that sharpens our theories. There are a few ways nature might manage it. Perhaps the disk around the young A star was rich and dense enough to build a giant quickly, before the companion could fully disrupt it. Perhaps the planet formed and then settled into the safe inner zone we described, where the companion's influence is weaker. Perhaps the two stars were arranged differently in their distant past, farther apart while the planet was forming, only later settling into their present close dance. Each of these is a possibility that scientists can explore. This is one of the angles that makes the discovery valuable beyond the simple thrill of finding a nearby world. A confirmed giant planet here would be a test case for our ideas about how planets are born in difficult places. It would push us to explain how a world this size came together under the gaze of a second sun. And because the system is so close, it is a test case we could actually study in detail, rather than guessing about from far away. It is worth saying plainly that this is unsettled science. We do not have a single agreed story for how a giant planet would form around Alpha Centauri A. We have a puzzle and several reasonable ideas, and a real example if it is confirmed to test them against. That honesty is part of the wonder. The discovery does not close a question, it opens several and hands us a nearby place to chase the answers. But all of this careful interpretation, the orbit, the formation, the moons, rests on the object being real and being a planet, rather than something else mimicking one. The team had to rule out the most stubborn impostor of all, a thing made not of a world, but of dust. When you find a faint point of light beside a star and call it a planet, there is a particular impostor you must rule out, and it is made of dust. Stars are often surrounded by faint clouds and disks of fine dust, and that dust glows in the infrared. A clump or ring of warm dust can, in principle, masquerade as a planet, or at least muddy the search, so the team had to take the dust seriously. To understand the worry, think about our own solar system. Spread throughout it, especially in the inner region, is a haze of fine dust, the debris of comets and colliding asteroids. On a very dark night, sunlight scattering off this dust can be seen from Earth as a faint glow, sometimes called the zodiacal light. It is gentle and easy to miss, but it is there. Our own system is not perfectly clean. It has its haze. Other stars can have the same kind of haze, sometimes much thicker than ours. We call this kind of dust around another star its own version of that glow, the dust that fills the inner part of a planetary system. If Alpha Centauri A were wrapped in a heavy shroud of such dust, that dust could glow in the infrared and complicate or even fake the signal of a planet. A bright enough dust cloud could be mistaken for an object, or could hide a real one in its haze. So an important part of the work was measuring how much such dust was actually present around Alpha Centauri A, and the answer turned out to be encouraging. The observations placed unusually tight limits on the amount of warm dust in the system. There was not a thick glowing shroud capable of producing or masking the kind of point of light they had found. The system appeared relatively clean of the dust that could have caused trouble. This matters in two ways. First, it strengthens the case that the faint point was a real, compact object, a planet, rather than a smudge of glowing dust. If there is little dust to glow, then a concentrated point of infrared light is more likely to be a genuine body. Second, the disappearing act could not be neatly blamed on dust either. A planet that vanishes and reappears is better explained by an orbit carrying it in and out of view than by dust drifting around, especially when the dust itself is so limited. There is a bonus to this clean result that reaches beyond the single planet. A system without much inner dust is, in a sense, a clearer window. Thick dust would not only confuse the search, it would also make it harder, in the future, to study any planets in detail, since their light would have to shine through the haze. A relatively dust-free Alpha Centauri A is therefore good news for the long project of understanding whatever worlds it holds. It is one less veil between us and the planet, so the dust question, which could have undermined the discovery, instead supported it. The system is clean enough that the faint point is hard to explain as anything but a real object, and the limits on dust are among the tightest measured anywhere. Another imposter ruled out, another reason to trust the planet. With the dust set aside, we can return with more confidence to the planet itself and ask about its character. We have called it a warm gas giant. Just how warm, and how does it compare to the giant planets we know best, the ones in our own backyard? Let us return to the planet's own nature and ask a simple question. How warm is it? The answer places it in an interesting spot among the worlds we know, and it required a careful correction along the way, which is itself a small lesson in how science works. When the discovery was first described, the planet's temperature was compared to Saturn's. That was a natural comparison, since the planet is roughly Saturn's mass and is a gas giant like Saturn. But a closer look showed that this first comparison undersold its warmth. The planet is in fact considerably hotter than Saturn, more than twice as warm. The early description was gently corrected as the analysis was refined. That correction is worth noticing, not as an error to dwell on, but as a sign of honest, self-checking work. Science adjusts itself. A first estimate is made, then revised as understanding improves and the revision is stated openly. The planet did not change, our description of it sharpened. Being warmer than Saturn fits the picture well, since this giant sits much closer to its star than Saturn sits to our Sun, bathed in more light and so kept warmer. Why is it warmer than Saturn? Two reasons work together. First, its orbit. Saturn lies far out from the Sun in the cold outer reaches at nearly 10 times the Earth-Sun distance. Our candidate planet orbits at only 1 to 2 times the Earth-Sun distance, far closer to its star so it receives much more warming light. Second, its own leftover heat. Giant planets hold warmth from their formation deep inside, and they glow gently with it for a very long time. The combination of starlight from nearby and internal heat from within makes this world warmer than the chilly distant Saturn we know. Its age is part of the picture too. Because Alpha Centauri A is about the same age as our Sun, several billion years old, the planet around it is likely mature, not freshly formed. A young giant planet just born glows hot with the heat of its making. An old one has had time to cool, so this planet is probably a settled, mature giant, warmed mainly by its nearness to its star rather than by the fierce heat of youth. In age and in general character, it may be the most similar to the giant planets of our own system, of any planet we have ever directly imaged. That similarity is part of why this object is so valuable. Many of the giant planets we have managed to photograph directly around other stars are young, hot, and far from their stars because those are the easiest kinds to see. A mature, temperate giant like this one, more like our own Jupiter and Saturn in age and disposition, is rarer and more precious as a point of comparison. It is closer to the familiar giants we have studied up close than most distant exoplanets are. So the portrait sharpens once more. A Saturn mass gas giant, mature in age, warmer than Saturn because it orbits near a Sun-like star, sitting on a stretched path in the temperate zone of the closest solar twin. Each detail makes it a more interesting object and a better mirror against which to compare the planets we know best. And the fact that we could draw such a portrait at all, from actual images rather than indirect hints, is itself extraordinary. Most planets beyond our system have never been seen as points of light. They are inferred, not pictured. To understand why directly imaging a planet is so rare and so prized, we should look at the art of it. We have now found close to 6,000 confirmed planets around other stars. That number is astonishing when you remember that, not so long ago, we knew of none. But here is a fact that surprises many people. Of all those thousands of planets, only a tiny handful have ever actually been seen, pictured as points of light. The vast majority were found by indirect means, never glimpsed directly at all. To appreciate the Alpha Centauri discovery, it helps to understand the difference. Most planets are found by watching their star, not the planet. One method, which we met earlier, watches for the star's tiny wobble as a planet tugs it back and forth. Another watches for the small regular dimming as a planet crosses in front of its star, blocking a sliver of light. Both methods are powerful, and both have found thousands of worlds. But in both, you never see the planet itself. You infer it from its effect on the star's light. Directly imaging a planet is a different and much harder thing. It means actually catching the planet's own faint glow as a separate point of light beside its star. It means doing exactly what we have been describing, blocking the star's overwhelming brightness and pulling the planet's whisper of light out of the glare. It is so difficult that only a small number of planets have ever been imaged this way, and most of them are special cases, young, hot, giant planets orbiting far from their stars where the contrast is most forgiving. That is what makes the Alpha Centauri candidate stand out. It is not a young, hot giant far from its star. It is a mature, temperate giant orbiting close to a sun-like star, the hardest kind of planet to image directly. If confirmed, it would be among the closest in directly imaged planets we have, sitting nearer to its star than almost any planet ever pictured. That is a real frontier. It is the kind of observation that the difficulty of the problem said should be nearly impossible, achieved at the very limit of what the instrument can do. There is something deeply satisfying about a direct image too, beyond its rarity. When you infer a planet from a wobble or a dimming, you are reading clues. When you image it directly, you are catching light that left the planet itself, light that glowed from that distant world and travelled 4 light years to be gathered by the telescope. It is as close to seeing the planet as we can get without going there. The point of light in that cleaned image is the planet's own glow, 4 years old by the time it reached us, captured and held. Direct imaging also opens doors that other methods cannot. Once you can isolate a planet's own light, you can begin, in principle, to spread that light out and study it, to read the makeup of the planet from the colours it gives off. That is how, in time, we might learn what a planet's atmosphere is made of, what gases it holds, what its clouds are like. For a planet this close, those possibilities are especially rich. A directly imaged world next door is a world we can keep returning to, learning a little more each time. So this discovery is not just one more planet on the long list. It is a hard-won example of the rarest kind of detection, applied to the nearest sun-like star at the very edge of what is possible. That it happened at all is a tribute to the instrument, yes, but also to the people who refuse to give up on a stubborn, glaring, vanishing target. Behind every faint point of light in an astronomical image, there are people. It is easy, in the wonder of the science, to forget that. So let us spend a chapter on the human side, on the team that chased this stubborn signal and would not let it go. The work was led by astronomers at major research institutions, with key roles played by scientists in the United States and in Europe. Among them was a graduate student who took on Alpha Centauri A precisely because it was one of the hardest objects he could find to work on. That is a telling detail. He was not handed an easy win. He went looking for the most challenging target available, and this nearest sun-like star, drowned in its own glare, was it? The difficulty was the appeal. There was also a senior scientist long associated with the search for planets around other stars, who helped lead the effort and who spoke about how demanding these observations were. He described them plainly as among the most challenging the team had attempted, because the stars are so bright, so close together, and move so quickly across the sky. That candour is worth honouring. These were not researchers overselling an easy result. They were people who knew exactly how hard the task was and said so. And there were the instrument builders, the people who, years before, had designed and built the mid-infrared instrument and its coronagraph. One of them, a European scientist who helped lead that instrument's development, recalled how, even while building the tool, the team had dreamed of pointing it at Alpha Centauri to see what they might find. For such people, this observation was the fulfillment of a long-held hope, a moment when a tool built years earlier finally did the very thing it had been imagined for. It is worth pausing on the operations teams too, the ones who designed the custom observing sequence just for this target. We mentioned that Alpha Centauri was too difficult for the standard routines, that the brightness and the speed across the sky required a special plan. Inventing that plan was its own quiet act of skill, the kind that rarely makes headlines but without which the discovery simply would not have happened. Their extra effort, as one scientist put it, paid off spectacularly. There is a lesson in all of this about how big discoveries actually come to be. We tend to imagine a single brilliant moment, a lone genius gasping at a screen. The reality is more collective and more patient. It is graduate students running millions of simulated orbits. It is senior scientists weighing every possible imposter. It is engineers who built an instrument years ago for exactly this dream. It is operations staff crafting a one-off plan for an impossible target. The faint point of light is the visible tip of a great deal of careful, shared human work. It is also a story of patience and honesty. The team did not announce a confirmed planet. They presented strong evidence for a candidate, laid out the detection and the non-detection side by side, explained the disappearing act with their orbit models, and use the careful word candidate throughout. They publish their findings for others to examine and challenge. That restraint is not weakness. It is the discipline that makes the eventual answer trustworthy, whichever way it falls. So when we look at that pixel beside Alpha Centauri A, we are really looking at the result of human curiosity, skill, and care stretched across years and continents. The planet, if it is real, has been there for billions of years. It took people like these to finally catch its faint light, and it is people like these who will now work to confirm it, which brings us to the careful matter of why it is still called a candidate. Throughout this story, we have been careful to use one word again and again: candidate. The object beside Alpha Centauri A is a candidate planet, not a confirmed one. That word is doing important work, and it is worth understanding exactly why scientists insist on it, even after all the evidence we have laid out. A confirmed planet is one that has been pinned down beyond reasonable doubt, usually by multiple independent detections that all agree, leaving little room for an alternative explanation. A candidate is something for which the evidence is strong and exciting but not yet conclusive, where there is still a real chance, however small, that the signal could be something else, or that the interpretation could shift. In this case, the reasons for caution are clear, and we have already met them. The strongest single piece of evidence is one detection in one observation. The other glimpses are an old, uncertain ground-based hint and two clean non-detections. The whole case rests on the argument that one stable orbit ties these moments together, an argument built on careful modelling. That modelling is convincing, but it is still a model. The object has not yet been caught, clearly and repeatedly, on its predicted path in a way that removes all doubt. There is also the basic fact that this is an extraordinarily hard observation, at the very limit of what the instrument can do. When you're working at the edge of capability, subtracting starlight tens of thousands of times brighter than your target, you must be especially humble. The very difficulty that makes the achievement impressive also demands extra care before declaring certainty. Good scientists treat their hardest results with the most caution, not the least. So what would it take to turn this candidate into a confirmed planet? The clearest path is to catch it again, more than once, at positions that match the predicted orbit. If future observations find the faint point reappearing right where the orbit says it should be, and moving along that path as time passes, the case would tighten dramatically. Each new detection at a predicted spot would make the dust, the artifact, and the chance alignment explanations less and less tenable until the planet stood confirmed. It might also help to see the planet in a different kind of light, with a different instrument or telescope, to confirm it is a real object with the properties expected of a warm giant, and to measure it more fully. A detection by an independent method or observatory, agreeing with what the mid-infrared images showed, would add great weight. Independent confirmation is the gold standard, and it is exactly what the team hopes to gather. There is no shame in the word candidate. On the contrary, it is a mark of integrity. The team could have reached for a bigger headline. Instead, they describe precisely what they had: strong evidence for a giant planet, and precisely what they did not yet have: final proof. They handed the result to the wider community to test. That is how the strongest knowledge is built, slowly and out in the open, with claims kept exactly as large as the evidence allows and no larger. The good news is that the means to settle the question are coming. New instruments and new telescopes are on the way, some designed for almost exactly this kind of target. The candidate will not stay a candidate forever in uncertainty. There are real plans to look again, and look harder. One of those plans involves a telescope built, in part, for systems just like this one. The story of this planet does not end with the telescope that found it. To confirm a candidate and study it properly, you often need more than one instrument, looking in more than one way. And as it happens, a new telescope is on the way that seems almost designed for this very task. It is called the Nancy Grace Roman Space Telescope, named for a pioneering astronomer often remembered as a mother of space-based astronomy. It is being prepared for launch in the coming years, with the aim of flying around the second half of this decade. When it flies, it will bring tools well suited to picking up where the current discovery leaves off. What makes it valuable here is that it carries dedicated hardware for exactly the hard problem we have been wrestling with, blocking the glare of bright stars to reveal faint objects beside them. It is built to test new techniques for imaging planets in difficult settings, including systems with more than one bright star, like Alpha Centauri. In other words, it is meant to do the kind of demanding observation that this discovery required, and to push it further. There is a second reason it matters, and it has to do with the kind of light it uses. The current discovery was made in infrared light, the heat glow of the planet. The new telescope would observe more invisible light, the kind our eyes see. Catching the planet in visible light would tell us different things than the infrared did. The infrared reveals the planet's warmth. Visible light, reflected sunlight from the planet, would reveal things about its size and how reflective it is, the nature of its clouds and surface of gas. Together, the two kinds of light would build a far fuller portrait than either could alone. Picture it this way. The first telescope felt the planet's warmth, like sensing the heat of a distant lamp. The next would catch the planet's reflected glow, like seeing the lamp's light bounce off it. One tells you how hot it is, the other tells you how big and bright and reflective. Combine them, and you begin to truly know the object, not just that it is there, but what it is like. So the plan, in broad strokes, is to keep watching. The team behind the discovery intends to use the current telescope again, to try to catch the planet returning along its predicted orbit. And when the new telescope is ready, it can join the effort, bringing its dedicated planet imaging hardware and its different kind of light to bear on the same nearby target. Between them, the case for the planet could move from strong evidence toward firm confirmation, and from a faint point toward a studied world. This is how the search advances, not in a single leap, but in a relay, one instrument handing the question to the next. The ground-based search caught the first whisper. The current space telescope caught the clear detection and worked out the orbit. The coming telescope may confirm it and fill in the details. Each tool does what it can, then passes the baton forward, and even the coming telescope is not the end of the line. Beyond it lie still larger and more capable instruments, both on the ground and in space, being built or planned to study nearby worlds in ever greater detail. Alpha Centauri A, as the nearest sun-like star, will be near the top of their target lists. The faint point of light found today is likely to be watched by a whole succession of future eyes. Look a little further ahead, and the future of this search grows even brighter. Beyond the telescope now being prepared, there are still larger and more powerful instruments being built and planned, both on the ground and in space, and the nearest sun-like star will be near the top of their lists. On the ground, a new generation of enormous telescopes is rising. These are observatories with mirrors far larger than anything operating today, tens of meters across, being constructed on remote mountaintops. A larger mirror gathers more light and sees finer detail, which means a better chance of separating a faint planet from its star. Equipped with advanced systems to sharpen their view through the atmosphere and with their own coronagraphs to block starlight, these giant ground telescopes are expected to be powerful planet hunters. Pointed at Alpha Centauri, they could add yet more glimpses of the candidate world, from a different vantage and with great light-gathering power. In space, the longer-term dreams are bolder still. Astronomers have begun planning a future observatory, whose central purpose would be to find and study planets that might be like Earth around other stars, including the search for signs of life. Such a telescope would be built from the ground up to do the hardest version of the task we have described, blocking the overwhelming light of a star to reveal small, faint, potentially habitable worlds beside it. For a mission like that, the nearest sun-like star is an obvious and precious target. Why does Alpha Centauri keep rising to the top of these lists? The same reason it always has: closeness. Every one of these future instruments will be able to do more with a nearby target than a distant one. The light is stronger, the angles are wider, the details are within reach. So as each new telescope comes online, it will naturally turn toward the star next door and toward whatever planets it holds. The candidate found today is likely to be revisited again and again by eye after eye, each sharper than the last. There is a lovely continuity in this. The questions we're asking about Alpha Centauri A will not be answered and then forgotten. They will be carried forward, refined, deepened. Is the candidate planet real? Future telescopes will likely settle it. What is it made of? They may begin to read its atmosphere. Are there other, smaller worlds in that system hidden for now? Larger instruments may find them. Could any moon be a home? That remains far off, but it is the kind of question these tools are ultimately reaching toward. It is worth stepping back to feel the shape of this. We are living at a moment when the nearest sun-like star has just yielded its first strong hint of a planet, and when a whole succession of ever more capable telescopes is arriving to follow up. The faint point of light we have spent this whole journey on is not an endpoint. It is an opening. It marks the beginning of a long and deepening study of the closest planetary system to our own that is not our own. And underneath all of this watching and planning lies an older, wilder dream, one that telescopes alone can never satisfy. Not just to see the nearest planets, but somehow to reach them. It is a dream far beyond our present power, and yet people have begun, seriously, to think about how it might one day be done. There is a dream that hovers behind all of this, older than any telescope, and we should give it an honest chapter. Not just to see the nearest planets, but to go to them. It is a dream far beyond our present power, and being clear-eyed about why is its own kind of wonder. We have said Alpha Centauri is a little more than 4 light-years away. Let us turn that into something you can feel. The fastest spacecraft humanity has ever launched move at speeds that, against the gulf between stars, are achingly slow. At the speeds of our current probes, a journey to Alpha Centauri would take not years, not centuries, but tens of thousands of years. A craft launched at the dawn of human civilization, at those speeds, would still be far from arriving today. The distance is not a barrier we can simply push through with more of the same. That is the sobering truth. Light crosses the gap in 4 years. Our machines, as they are, would take longer than all of recorded history many times over. Between the speed of light and the speed of our rockets lies an enormous gap, and closing it is one of the hardest problems anyone could pose. There is no easy fix, no near-term engine that turns 4 light-years into a human-scale trip. And yet people have begun to think seriously about it in modest first steps. One idea that has drawn real attention imagines sending not a great ship, but tiny feather-light probes, each weighing almost nothing, carrying just a sliver of instruments. The thought is to push these tiny craft with powerful beams of light from Earth, sails catching the push the way a boat's sail catches wind, accelerating them to a meaningful fraction of the speed of light. At such speeds, the journey would shrink from tens of thousands of years to mere decades. A probe launched in a person's youth might send back data within their lifetime. It is important to be honest about the status of such ideas. They are early, ambitious, and unproven. The engineering challenges are immense, from building sails that survive the beam, to aiming across light years, to gathering and sending back any useful signal from so far away. No such probe is anywhere near ready to fly. This is a dream in its first sketches, not a mission on a launch pad. We should hold it as a hopeful possibility, not a promise. But the dream is not idle, and the discovery we have been following gives it a sharper point. A target gives a dream direction. For a long time, even the boldest thoughts of reaching another star had no specific world to aim for. Now, around the nearest sun-like star, there may be a planet, and around the faint red dwarf nearby, there are others. Suddenly the dream of going there has destinations, real places that a probe, if we ever built one, could be sent to study up close. Whether humanity ever sends anything across that gulf is utterly unknown, and may lie far beyond our own lifetimes, if it ever happens at all. The honest stance is humility before the distance, but there is something quietly powerful in simply knowing that the nearest system holds worlds, and in beginning, however tentatively, to imagine reaching them. The planets give the dream a shore to aim for, even if the crossing remains beyond us. For now, though, our reach is light, not travel. We cannot go to Alpha Centauri. We can only gather its light and read it carefully. And that, it turns out, is enough to change a great deal, which is where we turn as our journey nears its end. As we near the end of our journey, it is worth stepping back to ask what this one faint point of light could change. Why does a single candidate planet around one nearby star matter so much in the larger story of our search for other worlds? The first answer is closeness, the theme that has run through everything. If confirmed, this would be among the closest planets we know around a star like our Sun, and the nearest directly imaged planet of its kind. That nearness makes it a touchstone, a planet we can return to again and again with our best instruments, learning more each time. Most exoplanets are too far to study in depth. This one would be near enough to become a laboratory, a place where we test our tools and sharpen our understanding of what planets around Sun-like stars are really like. The second answer is what it teaches about planet formation. We have seen how building a giant planet in a close two-star system was thought to be difficult, perhaps even unlikely. A confirmed giant here would tell us that nature finds a way even in such restless places. That would reshape our theories about where planets can form and survive. It would say that planetary systems are even more common and more robust than we thought, taking hold even in settings we once considered too chaotic. That is a meaningful shift in how we picture the galaxy's worlds. The third answer is about method, about the very act of seeing. This discovery pushes direct imaging, the rarest and hardest kind of planet detection, to a new frontier, catching a mature, temperate giant close to a bright sun-like star. Each time we achieve something at the edge of what is possible, we expand what becomes routine for the next generation of instruments. The hard-won techniques used here, the custom observing plan, the careful starlight subtraction, the orbit modelling that turned a disappearance into a confirmation, all become part of the toolkit for finding fainter, smaller, more Earth-like worlds in the future. And there is a fourth answer, quieter and more human. This discovery is a reminder of how the search for other worlds actually progresses, not in a single triumphant flash, but in patient, honest steps. A faint hint from the ground, a careful detection from space, a mystery faced openly, a clever resolution, a candidate announced with integrity, handed to the community to test, with the means to confirm it already on the way. It is a model of how good science is done, and a sign that the search is healthy and advancing. Put these together, and you see that the importance of this faint point reaches far beyond itself. It is one planet perhaps around one nearby star, but it is also a test of our theories, a frontier for our methods, a touchstone for future study, and a destination for our oldest dreams of reaching beyond the sun, a single pixel carrying all of that. It is easy, amid the science, to lose the simple feeling underneath. So let us set the details down for a moment and remember where we began. We started by looking up at a single point of light in the southern sky, the nearest star system to our own, and wondering whether anything orbited there. We have travelled a long way through telescopes and orbits and dust and dreams. Now it is time to return, gently, to that point of light and let the wonder settle. We began this journey by asking you to look toward the southern sky, at a single bright point called Alpha Centauri. It looked like one star. We have learned, over these chapters, that it is three. We have learned that one of them is almost a twin of our own sun, and we have learned that beside that twin, in a faint mid-infrared glow, 10,000 times dimmer than the star, there may sit a planet, the closest such world we have ever glimpsed around a star like ours. Think back over what that faint dot of light has carried us through. We saw why the nearest system was always the most tempting prize, and why it was also the hardest to reach, drowned in the glare of two bright stars. We met the telescope cold and far from Earth, and the instrument built to block a star and reveal what hides beside it. We watched the planet appear in one careful observation, then vanish in two more, and we followed the patient detective work of 1,000,000 simulated orbits that turned that disappearance into proof rather than doubt. We drew the planet's portrait, a gas giant about the mass of Saturn, warmer than Saturn, mature in age, swinging on a stretched orbit between about 1 and 2 times the Earth-Sun distance, sitting in the temperate zone of the nearest Sun-like star. We were careful, as the scientists are, to call it a candidate, and to hold honestly both the strength of the evidence and the proof still to come. We looked ahead to the telescopes that may confirm it, and to the distant dream of one day reaching toward it. And through all of that, the thing itself remained simple, a faint point of light beside a star, light that left that distant world and travelled 4 years across the dark to be gathered, at last, by a telescope built by human hands. When you hold that in mind, the whole story folds back into a single image, a spark beside a sun, 4 light-years away, that we managed to see. It is worth sitting with how strange and lovely that is. For most of human history, Alpha Centauri was just the foot of the Centaur, a bright marker in the southern sky, watched and named but never truly known. Now, in our own time, we have leaned in close enough to find, beside one of its stars, the possible glow of a planet. The nearest sun-like star may not be alone. It may have a world. Whether that world is finally confirmed, and whatever it turns out to be, something has already shifted. The nearest doorway to the rest of the universe is no longer just a doorway of stars. It may be a doorway of planets too. The closest place that is not home may itself have a home of sorts circling it, a giant world, and perhaps, in dreams we cannot yet test, a moon. So the next time you find yourself under a dark sky, and you think of that point of light low in the south, remember what hides inside it. 3 stars turning slowly around each other, a twin of our own sun, and beside that twin, caught at the very edge of what we can see, a faint and patient glow that may be the nearest planet to us around a star like ours. No one was quite ready for it, and there it was, waiting in the light all along.